How do we describe gases mathematically, and what is the ideal gas law? We're going to answer these questions, but first we're going to do an experiment. Let's take a look at this PhET simulation for gases. First, we're going to look at how temperature affects pressure. We're going to keep the volume constant. As I increase the temperature, notice how the pressure increases. It's 76. I increase the temperature. Now the pressure is 84. So as you increase temperature, the pressure also increases. Next, I'm going to look at how volume affects pressure. We're going to keep the temperature constant. And as I decrease the volume, the pressure goes up. And as I increase the volume, the pressure goes down. So they kind of change in opposite ways there. That suggests that there may be an inverse relationship. Next, we're going to look at volume and temperature. We're going to keep the pressure the same, and I'm going to change the volume. I'm going to make it smaller. Let's see what happens to the temperature. So as I decrease the size of the cylinder, decrease size of the volume, notice that the temperature goes down. As I increase the volume, the temperature goes up. Lastly, I'm going to look at how changing the number of molecules in here affects the volume. We're going to keep the pressure and the temperature the same. I'm going to have to manually do this with the volume because I can't control the pressure directly. So I'm going to add some more gases in here, gas particles in here. Remember, this is about 80 right here, okay? So I'm going to add some more. I'm going to add some more. Okay, now we want to get this back to 80. Let's see if the volume is going to be smaller or bigger. If I go this way, no, that doesn't work. I'm going to go the other way and trying to get it closer to 80. So as I add more gas particles, the volume increases. So that suggests there may be a proportional relationship. Here are the four relationships that we just explored in the PhET simulation. We'll start with Boyle's law, which states that P1V1 is equal to P2V2, which basically means that the pressure is inversely related to the volume. The constants are temperature and the number of particles. Charles's law states that V1 over T1 is equal to V2 over T2, which basically means that the volume is proportional to the temperature. The constants are pressure and the number of particles. Avogadro's law states that V1 over N1 is equal to V2 over N2, which basically means that the volume is proportional to the number of particles. The constants are pressure and temperature. And Gay-Lussac's law states that P1 over T1 is equal to P2 over T2, which basically means that the pressure is proportional to the temperature and the constants are volume and the number of particles. If we combine these relationships, we get the ideal gas law, which states that PV is equal to nRT. Now let's take a look at these variables individually. First, we'll start with pressure. So pressure is the force per unit area due to molecular collisions. The units for pressure is pascals, and 1 pascal is equal to 1 Newton per meter squared. That makes sense because force unit is Newton, and area unit can be meters squared. 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. The ideal gas law uses the absolute pressure. So if you're given the gauge pressure, make sure you add the atmosphere pressure to get the absolute pressure. V stands for volume, and volume is the space the gas occupies. The unit for volume is meters cubed, not liters. If you get liters, make sure to convert it to meters cubed. Next, we're going to take a look at N, which stands for the number of moles. So moles is like a counting unit, just like a dozen represents 12. A mole represents 6.022 times 10 to the 23rd molecules. This number is real special. It has a name. We call it Avogadro's number. The symbol is capital N, subscript A. Capital N is the total molecules, and the relationship is the number of moles is equal to the total number of molecules divided by Avogadro's number. Capital R is the universal gas constant, which is 8.31 joules per Kelvin per mole. Sometimes you'll get a different number depending on the units, but the value is the same. Boltzmann's constant is K sub B and is equal to the universal gas constant divided by Avogadro's number. And the value is 1.38 times 10 to the negative 23rd joules per Kelvin. So when would you use the universal gas constant? When would you use Boltzmann's constant? Well, if you're working with moles, then you're going to use the universal gas constant. But if you're working with individual molecules, then the Boltzmann constant would be easier to work with. If you're using Boltzmann's constant, then the equation becomes PV is equal to NKB times the temperature. Temperature is proportional to the average kinetic energy per molecule. The unit for temperature is Kelvin. So if you get a number in Celsius in the problem, make sure you add it to 273.15 to convert it to Kelvin. So when can you use the ideal gas law and when can you not use the ideal gas law? We're going to compare the ideal gas versus real gas because gases are not always ideal. First, ideal gases are particles that have no volume. Real gases, particles do take up space. Ideal gases, there are no intermolecular forces. Real gases, particles can attract and repel. In an ideal gas, collisions are perfectly elastic. That means there's no loss in kinetic energy. In real gases, there are small energy losses that can occur. In an ideal gas, there's random constant motion, but in a real gas, motion can be affected by intermolecular forces. And lastly, in an ideal gas, it obeys PV equals nRT. In a real gas, it deviates from the ideal gas law at high pressures and low temperatures. Now let's take a look at a problem. The gauge pressure in your car tires is 2.5 times 10 to the 5th newtons per meter squared at a temperature of 35 degrees Celsius. When you drive it onto a ferry boat to Alaska, what is their gauge pressure later when their temperature has dropped to -4 degrees Celsius? First, we're going to write down what's given. So we're given the gauge pressure, 2.5 times 10 to the 5th newtons per meter squared. But what we need is the absolute pressure. Remember that the ideal gas law uses the absolute pressure. So we need to take this value and add it to 1.013 times 10 to the 5th newtons per meter squared. And we get 3.513 times 10 to the 5th newtons per meter squared. Next, we're given the temperatures. We need to convert the temperatures in Celsius to Kelvin. So we need to add 273.15. And we get that T1 is 308.15 Kelvin. T2 is 233.15 Kelvin, and we're looking for P2. The ideal gas law is PV equals nRT, where we know that the number of molecules is going to stay the same. It's inside the tire. R is constant. V is the volume tire, which is going to be constant. So I can isolate P and T and rewrite this as P1 over T1 is equal to P2 over T2. And what we're looking for is P2. So then I can isolate P2. Next, I'm going to substitute P1, T2, and T1. And we get that P2 is equal to 2.658 times 10 to the 5th newtons per meter squared. Remember that this value is the absolute pressure, and we're looking for the gauge pressure. So we need to subtract the atmospheric pressure, which is 1.013 times 10 to the 5th, and our gauge pressure is 1.64 times 10 to the 5th newtons per meters squared. Next question. An airplane passenger has 100 cubic centimeters of air in his stomach just before the plane takes off from a sea-level airport. What volume will the air have at cruising altitude if the cabin pressure drops to 7.5 times 10 to the 4th newtons per meter squared? First, we're going to write down what's given. So we're given that V1 is equal to 100 cubic centimeters. The pressure is at sea level, so we're going to use 1.013 times 10 to the 5th newtons per meter squared. That's atmospheric pressure. We're looking for V2, and we're given that P2 is 7.5 times 10 to the 4th newtons per meter squared. Starting with the ideal gas law, we know that the N, the number of particles, is going to stay the same, and the temperature is going to stay the same. We're assuming that it's just going to be body temperature here. And what's changing is the pressure and volume. So we can write P1 V1 is equal to P2 V2. We're solving for V2. So V2 is equal to P1 V1 over P2. We're going to substitute P1 V1 and P2, and we get 135 cubic centimeters. If you found this video helpful, check out my next video on kinetic theory.